In this lecture, I would like to discuss about surface chemistry. Unit 4th. Surface chemistry is a branch of physical chemistry that deals with the properties of surfaces and with the chemical reactions occurring at a surface. So whatever reactions which are takes place onto the surface of the substance, that comes into the surface chemistry. So what type of the phenomenon is takes place onto the surface of the substance? That phenomenon, it is adsorption. So what is adsorption? Adsorption, it is the accumulation of molecular species at the surface of the solid. Adsorption, it is the accumulation of molecular species at the surface of the solid, or it is also the concentration of the substance onto the another substance, onto the surface of the another substance, that is called as adsorption. Now in this process of the adsorption, one molecule get adsorbed onto the other molecule. Now what is the adsorbate? The molecular species or substance which concentrates or accumulates at the surface is termed as adsorbate. For example, adsorption of hydrogen on nickel. So hydrogen gas, it acts as a adsorbate. Now the another term, it is adsorbent. The material on the surface of which the adsorption takes place is called adsorbent. The material on the surface of which the adsorption takes place is called adsorbent. Adsorption, it is a surface phenomenon. Generally, on the surface of the solid, the gaseous molecule gets adsorbed. So solids are in finely divided state and they must have the large surface area. Therefore, they can absorb the adsorbate molecule on it. The examples of the adsorbent are charcoal, silica gel, alumina gel, clay, colloids, metals. So most of the transition metals are acts as a adsorbent. They are acts as a catalyst. And on the surface of the catalyst, many reactions are takes place. For example, nickel, platinum, palladium. These transition elements are a very good catalyst because they can absorb the substance on it. So let us show this adsorption phenomenon onto the another screen here. So you can see here. Suppose, let us consider this is a nickel metal acts as a adsorbent. It acts as a adsorbent, and on the surface of this nickel, the hydrogen gas get adsorbed. So in this case, hydrogen gas, it is a adsorbate. Hydrogen gas, it is called as adsorbate, and nickel metal, nickel solid, it is called as adsorbent, and the process is called as adsorption. So on the surface of the metal, the gaseous molecule gets adsorbed. So this is also called as adsorption of gases onto the surface of the metal. So thus, adsorption, it is a surface phenomenon. So on the surface of the metal or other substances, the molecules who are going to be adsorbed, they will react, and the chemical reaction maybe takes place onto the surface of the adsorbent. Now let us discuss about the desorption. Desorption, it is totally opposite to that of the adsorption. In adsorption process, the molecule gets accumulate on the surface of the adsorbent, while in the desorption process, the adsorbed molecules leave the surface. So you can see here the process of removal of an adsorbed substance from the surface of the adsorbent is called desorption. Suppose that on the nickel surface, some of the hydrogen gaseous molecule get adsorbed. Okay. Now they are not permanently adsorbed. So some of the molecules leave the surface of the adsorbent. So the process of removal of adsorbed substance from the surface of the adsorbent, it is called as desorption. So desorption, it is a opposite to that of the adsorption. Next term, heat of adsorption. The amount of heat evolved per mole of the adsorbent adsorbed is called heat of adsorption. So during the adsorption process, whatever the heat energy is released, whatever the heat energy is evolved per mole of the adsorbate, it is generally called as a heat of adsorption. Adsorption, it is a exothermic process. Adsorption, it is a exothermic process where the heat energy is liberated to the surrounding. Now let us going to discuss the types of the adsorption. So first type, it is physical adsorption, and second type, it is chemical adsorption. Okay. So let us see now here. In physical adsorption, due to weak van der Waals forces between the adsorbate and adsorbent, uh, the physical forces are existing there. Now in chemical adsorption, there is a loose chemical bond between the surface of the adsorbent and adsorbate. Okay. Then in physical adsorption, it is particularly non-specific. It is highly specific. Physical adsorption, it is a reversible process. Chemical adsorption, it is a irreversible process. During physical adsorption, there is a formation of the multilayer of adsorbate. And during the chemical adsorption, there is a formation of only one layer, unilayer on the surface of the adsorbate. Physical adsorption generally takes place at low temperature and high pressure. And chemical adsorption, it is takes place at high temperature. In case of physical adsorption, activation energy is low. In case of chemical adsorption, activation energy is high. So thus there are two types of the adsorption processes. One, it is a physical adsorption, that is takes place due to the van der Waals forces, that is takes place due to the physical forces which are existing on the surface of the adsorbent. And chemical adsorption, it is due to the formation of the chemical bond by the transfer of the electrons between the adsorbent and adsorbate. So there exists a loose chemical bond between the adsorbent and adsorbate. Now you should be remember that the chemical adsorption, it is highly specific. It means on the particular adsorbent, the particular gaseous molecule can be adsorbed. Okay. While physical adsorption, it is non-specific. It is reversible. It is irreversible. Okay. And one of the important thing is that the physical adsorption is a multi-layer adsorption process. It means that on the surface of the adsorbent there is a formation of many layers. But in chemical adsorption there is a formation of only one layer, that is unilayer of adsorbate. Physical adsorption, it is takes place at low temperature and high pressure, while chemical adsorption, it is takes place at high temperature. So let us proceed further. Langmuir's adsorption isotherm. So I would like to discuss here the Langmuir's adsorption isotherm. What is adsorption isotherm? Adsorption isotherm, it is the equilibrium relation between the amount of the gas adsorbed per unit mass of the adsorbent with pressure. It is the relation between amount of the gas adsorbed. Suppose that X is the amount of the gas adsorbed and M is the mass of the adsorbent. So adsorption isotherm, it is the amount of the gas adsorbed per unit mass of the adsorbent, and it is related to the equilibrium pressure. Okay, that is the adsorption isotherm. So first adsorption isotherm, that is Freundlich adsorption isotherm. It is Freundlich adsorption isotherm. So according to Freundlich adsorption isotherm, the amount of the gas adsorbed per unit mass of the adsorbent, it is directly proportional to pressure. It is directly proportional to pressure. So according to this adsorption isotherm, we can write the equation here, that is X upon M, that is X is the amount of the gas adsorbed and M is the mass of the adsorbent. It is equal to Kp raised to 1 upon N, where K is called as a constant here, and the value of 1 upon N, it is equal to 0 to N, 0 to 1. Okay, so this is the Freundlich adsorption isotherm. But actually there are so many limitations in the Freundlich adsorption isotherm. These are the limitations are given here. The equation put forward by Freundlich was entirely an empirical relation with theoretical background. It has no any experimental proof. It means this equation, the amount of the gas adsorbed per unit mass of the adsorbent, it is equal to Kp raised to 1 upon N. So this is not having any experimental proof. It is a theoretical background. The Freundlich equation was valid only at low pressure. This equation should be true at low pressure, means amount of the gas adsorbed per unit mass of the adsorbent is directly proportional to the pressure, but it is only at low pressure. The value of the constant in Freundlich equation, it is found to be temperature dependent. So these are the certain limitations in the Freundlich adsorption isotherm. So that's why the Langmuir's adsorption isotherm was developed. And in Langmuir's adsorption isotherm, the limitations of the Freundlich adsorption isotherm can be minimized. So you can see now, what are the assumptions of Langmuir's adsorption isotherm, or what are the postulates of Langmuir's adsorption isotherm? So see here the assumptions of Langmuir's adsorption isotherm. Okay. So first assumption, according to the Langmuir's theory, all gases under study are assumed to be behave ideally. All the gases shows the ideal behavior. The adsorbed layer of gas molecules on the surface of the adsorbent is assumed to be unimolecular in thickness. According to the Langmuir's theory, there is only one layer, it is formed on the surface of the adsorbent. Suppose that this is adsorbent and gaseous molecules are adsorbed here. So there is a formation of only one layer onto the surface of the adsorbent. So it is a unimolecular in thickness, or it is a unilayer process. The adsorbed layer of gas molecule on the surface of the adsorbent is assumed to be unimolecular theory. Therefore, Langmuir's theory is also called as Langmuir's unimolecular adsorption process. Now, third assumption, the gas molecules are adsorbed on selective sites present on the surface of the adsorbent. Whatever the gas molecules are adsorbed here, they are going to be adsorbed onto the selective sites of the adsorbent. One site can adsorb only one molecule. Whatever the sites are available here, actually on the surface of the adsorbent, there are such sites are available. Okay, and onto that such sites, the gaseous molecules get adsorbed. So the gas molecules are adsorbed on selective sites present on the surface of the adsorbent. Now, the bond between the gas molecules. This is the very important assumption of the Langmuir's adsorption isotherm. The bond between the gas molecule and adsorbent may be physical or chemical. Mostly it is chemical. Mostly it is chemical because the Langmuir's theory suggested that there is a loose chemical bond between the adsorbate and adsorbent molecule. Okay, so this is the important assumption of the Langmuir's theory. The fifth assumption you can see here, the amount of the gas molecule adsorbed on the surface of the adsorbent depends upon the surface area of the adsorbent. The amount of the gas molecules adsorbed on the surface of adsorbent depends on the surface area of the adsorbent. You can see here, let us take the example here. Suppose we have the platinum adsorbent. Platinum. This is the surface of the platinum. Okay. Platinum metal or platinum solid. Now onto the surface of the platinum, the gaseous molecule gets adsorbed and there is a formation of unimolecular layer on the surface of the adsorbent. So gaseous molecules are adsorbate. So they are going to be adsorbed here. So according to the Langmuir's theory, there is a loose chemical bond. This bond is a loose. But there is a chemical interaction between the surface of the adsorbent and these gas molecules. Okay. So whatever the surface area of the adsorbent it is covered, that surface area is called as theta. Theta is the surface area covered by the gaseous molecules. Okay. So you can see here, the amount of the gas molecule adsorbed on the surface of the adsorbent depends upon the surface area of the adsorbent. Next assumption, the heat of adsorption is same for all sides. It is generally independent on the fraction of the adsorbent surface covered by the gas molecules. Next assumption, which is very important, the rate of adsorption of gas molecules on adsorbent surface is proportional to the uncovered surface area of the adsorbent. The rate of adsorption of gas molecules on adsorbent surface is proportional to the uncovered surface area of the adsorbent. Whatever the surface area is available for the adsorption process, the rate of adsorption will be greater. So more the surface area, more the rate of adsorption. Less the surface area, less is the rate of adsorption. So it will depends upon the uncovered surface area of the adsorbent. Next assumption, adsorption it is a dynamic process consisting of two opposite actions. Condensation or adsorption of gas molecules on the surface of the solid and desorption of the gas molecule from the solid surface. Okay, so you can see here, adsorption it is a dynamic process. That is, the molecules get adsorbed. Molecules get adsorbed on the surface of the adsorbent. For example, onto the platinum surface, suppose nitrogen gas is adsorbed. Nitrogen gas is adsorbed here. Now, the adsorbed nitrogen molecules, some of the nitrogen molecules leave the surface. That process is called as desorption. That is called as desorption. So there is a dynamic process. That is rate of adsorption. Rate of adsorption becomes equal to the rate of desorption. Becomes equal to the rate of desorption. Okay, that is, there is a dynamic equilibrium. At equilibrium stage, the rate of adsorption becomes equal to the rate of desorption. So these are the assumptions of the Langmuir's adsorption isotherm. Okay. So last assumption is important here. Adsorption, it is a dynamic process consisting of two opposite actions. First one, it is adsorption of gas molecules on the solid surface, and second one, it is the desorption of the gas molecules. Those molecules who are adsorbed, some of the molecules leave the surface. That process, it is called as a desorption process. Now, on the basis of this, I would like to derive here the Langmuir's adsorption isotherm. Consider the phenomenon of adsorption of gas on the surface of the solid adsorbent. Now it is clear that the gaseous molecules gets adsorbed onto the solid surface. Let theta be the fraction of the surface covered by the gas molecule. Theta be the fraction of the surface covered by the gas molecule. Suppose that this is the surface of the adsorbent available for adsorption process, or in another way we can represent this in this way also. This is the surface of the adsorbent available for the adsorption process, and some part of this area, it is covered by the gas molecule. So this is called as theta. So let theta be the fraction of the surface covered by the gas molecule. Okay, theta be the fraction of the surface covered by the gas molecule. So this is theta, and this is the remaining surface area. Okay, and rate of adsorption, it will depends upon the uncovered surface area of the adsorbent. So let us write here the fraction left uncovered. Suppose that this is unit surface area and theta is the surface area covered. So this is theta. So it is 1 minus theta. So the fraction left uncovered, it is equal to 1 minus theta. So according to the kinetic theory of the gases, the rate of adsorption, it is directly proportional to the pressure. As we increase the pressure onto this gaseous molecule, the adsorption will be increases. So rate of adsorption, it is directly proportional to the pressure, as well as according to the assumption, the rate of the adsorption, it is directly proportional to the uncovered surface area. More the uncovered surface area, the adsorption process will be greater. So therefore, we can write here rate of adsorption, it is directly proportional to the uncovered surface area as well as pressure. So taking here proportionality constant Ka, it is 1 minus theta into P. K is called as a proportionality constant, or it is a constant for adsorption. A stands for adsorption. P is the pressure of the gas. Okay. Now let us see the rate of desorption. Whatever the surface area covered by the gaseous molecules here, so rate of desorption will depends upon the surface area covered by the gaseous molecules. Therefore, we can write here rate of desorption, it is directly proportional to the theta. The molecules which are leaving from the surface, it will ultimately depends upon the surface area covered by the gaseous molecules. Once the surface area is covered, that gaseous molecule escape from the surface. That gaseous molecule desorb from the surface. So rate of desorption, it is directly proportional to the surface area covered by the gaseous molecule. So we can take here the proportionality constant. So rate of desorption, it is equal to Kd into theta, where Kd, it is the Kd, it is the proportionality constant for desorption. Okay. At equilibrium, we know that the rate of adsorption becomes equal to the rate of desorption. So rate of adsorption, it is the equation for rate of adsorption, it is equal to Ka into 1 minus theta into P. It is Ka into 1 minus theta into P, rate of adsorption. This is equation 1. And rate of desorption, it is Kd into theta, because at equilibrium both rates are equal. Simultaneously, the adsorption and desorption processes are takes place there, and at equilibrium the rate of adsorption becomes equal to the rate of desorption. So we can write here Ka into 1 minus theta into P, it is equal to Kd into theta. So we can simplify this. Ka into P minus Ka into theta into P, it is equal to Kd into theta. So they take this term onto this side, it becomes positive here. So K into P, it is equal to Kd into theta plus this now here, K into theta into P. Now theta is common here. So theta into Kd plus K into P. So according to this, we can find out the theta here. So theta it is equal to now. What is theta? Theta it is the surface area covered by the gaseous molecule. So theta it is equal to here Ka into P divided by Kd plus divided by Kd plus Ka into P. Kd plus Ka into P. So suppose that this is the equation 3 now here. So we can find out here the surface area covered by the gaseous molecule, that is theta, and which is related to the pressure. So let us proceed further. So we already write here theta, it is equal to K into P divided by Kd plus K into P, equation 3. Now dividing this equation on RHS side by Kd, both to the numerator and to the denominator. Okay. So we can write the next step of the equation, that is theta it is equal to, so you can see here, so this K divided by Kd, so K upon Kd into P, Kd divided by Kd plus K upon Kd. So now it is, in this case, K upon Kd, K is constant, Kd is also constant, so constant divided by constant is another constant. So let us take here B, B it is equal to K upon Kd. So B into P divided by, this is 1 plus B into P. So therefore we are getting the equation here, theta it is equal to B into P divided by 1 plus B into P. B is another constant here, B into P. You can see this equation, equation 4 here. So let us proceed further. If V is the volume of the gas adsorbed per unit mass of the adsorbent, see, we are having the adsorbent molecule, adsorbent solid substance. So this is adsorbent. Okay. If V is the volume of the gas adsorbed, now whatever the volume of the gas is adsorbed here, so V is the volume of the gas adsorbed per unit mass of the adsorbent, whatever the mass of this, and Vm is the volume of the gas required for the formation of the single layer. So to cover this total surface area, that is Vm, Vm is the volume of the gas required for the formation of the single layer over the adsorbent. So that is Vm. So try to understand here the difference between V and Vm. Vm, it is the volume of the gas required for the formation of the single layer, and V is the volume of the gas adsorbed. Okay, means it is V here, and Vm it is the total volume of the gas required for the formation of the single layer on the surface of the adsorbent. So what is theta? How we can calculate the theta here? So theta it is equal to V upon Vm, where V it is the volume of the gas adsorbed divided by, because theta is the fraction, it is the fraction of the surface covered by the gaseous molecule. So how we can calculate that fraction? So Vm it is the volume of the gas required for the formation of the single layer to cover this all the layer, that is Vm. Out of that, this much get adsorbed, V get adsorbed. So theta is, it is the fraction of the surface covered by the gaseous molecule. So this is the fraction of the surface covered. So out of this Vm, this V can be covered by the gaseous molecule. So theta it is equal to V upon Vm. So try to understand about this. This is equation 5. Substituting equation 5 in equation 4. Okay, so previously we have written theta it is equal to b into p divided by 1 plus b into p. So we can put now theta it is equal to v upon vm. So we are getting this equation v upon vm it is equal to b into p divided by 1 plus b into p, where b is a constant here. Now let us simplify this equation. V it is equal to, so this v will be here vm into b into p divided by 1 plus b into p. Let us simplify this equation, this. Okay, so this equation can be simplified as, we have to see here v into 1 plus b into p, it is equal to vm into b into p. Okay, so taking this v on this side, so this is p upon v, and taking this vm into b on this side, so we can write now here, so it is p upon v it is equal to 1 upon p upon v it is equal to, we can write this equation now, 1 plus bp divided by this vm into b, vm into b, plus p upon vm, plus p upon vm. We are getting this equation p upon vm. Okay, so this is equation 6 here. This equation it is called as equation 6. So equation 6 is known as Langmuir's adsorption isotherm. This is nothing but the Langmuir's adsorption isotherm. Okay, once again we are repeating the step number 5, 6. So you have to see here how we will get the Langmuir's equation, Langmuir's adsorption isotherm. We know that theta it is equal to b into p divided by 1 plus b into p, and theta it is equal to v upon vm, where v is the volume of the gas adsorbed per unit mass of the adsorbent, and vm it is the volume of the gas required to cover the total surface area of the adsorbent, and theta is the fraction of the surface covered by the gaseous molecules. So now put here theta, so we can write here v upon vm it is equal to b into p divided by 1 plus b into p. So we can simplify this equation now. V it is equal to, so taking this vm here on this side, so here vm into b into p divided by 1 plus b into p. Doing the cross multiplication of this, so it is v into 1 plus b into p, it is equal to vm into b into p, where b is a constant here. Now dividing this by vm into b, okay, dividing this term by vm into b and this term by v. Okay, so we can write here dividing this term or taking this v on this side or vm upon b on this side. So dividing the LHS term by vm into b. So we can write here now the equation in this way, p upon v it is equal to, p upon v it is equal to, so this equation can be written as 1 upon vm into b, 1 divided by this vm into b, plus it is written as this is b into p divided by vm into b. So this is written as p upon vm, p upon vm, b get cancelled there. So this equation is called as Langmuir's adsorption isotherm. Langmuir's adsorption isotherm. So try to understand about this. Langmuir's adsorption isotherm. Once again, you have to see the modification here. This term taken on this side, okay, and V should be on this side, okay. So it is Vm upon B at the denominator. Once again, you have to see here, if you have some doubt here, 1 plus B into P divided by Vm into B, it is equal to, it is P upon V. So we can write here P upon V, it is equal to, this is 1 divided by Vm into B plus Bp divided by Vm, B get cancelled. So it is P upon Vm. So this equation, it is called as Langmuir's adsorption isotherm. Okay. Langmuir's adsorption isotherm. This is the equation which is called as Langmuir's adsorption isotherm. Okay. So try to understand about this. Now there are two cases are applicable. In this equation, first of all, let us write that equation here. Previously we are having the equation here, that is P upon V, it is equal to 1 upon Vm into B. That equation should be written as P upon V into 1 upon Vm into B. So let us see this equation now. Langmuir's equation, that is P upon V, it is equal to 1 upon Vm into B plus P upon what? Vm. Okay. This is the Langmuir's equation. At very low pressure, the term Bp in the denominator, or you can take the another form of the Langmuir's equation. This. Let us take this equation. V, it is equal to Vm into B into P divided by 1 plus Bp. So let us take this equation. Instead of modifying this equation, we can take the another equation here. That is, you can see here that equation, it is V equal to Vm into B into P. V, it is equal to Vm into B into P. So we can write that equation now in this way. You can see here. So that equation, it is V upon Vm into B into P divided by 1 plus Bp. Okay. So we modify this equation, therefore V, it is equal to Vm into B into P divided by 1 plus Bp. This equation, this is also called as a Langmuir's equation. At very low pressure, the term Bp in the denominator of equation 6, suppose that this is equation 6. If the pressure is very low, so if the value of the pressure is very low, 1 plus this Bp, so Bp in the denominator of the equation 6 acquires very less value compared to unity. Hence, it can be neglected. Okay, it can be neglected. So this is 1 plus B into P, it is approximately equal to 1 because pressure becomes very, very low. So we can write here V equal to Vm into B into P. This is equation 7. So that is volume of the gas adsorbed. This is V is the volume of the gas adsorbed is directly proportional to the pressure of the gas. It is related to the pressure. V is directly proportional to the pressure of the gas here. Okay. At very low pressure, it is related to the pressure. Now at very high pressure, the term Bp in the denominator of the equation 6 means into this equation is very large as compared to unity. At very high pressure, Bp should be very high. Bp value should be high, this value. Okay. So one will be neglected there. So we can write the equation now. This is V equal to Vm into B into P divided by, now this one, it is neglected. Pressure is very high. So 1 plus Bp, it is equal to Bp, B into P. So we can write here B into P. So in this equation, B into P, B into P. So V, it is equal to Vm. Okay. That is volume of the gas adsorbed is independent of the pressure. So it indicates that at higher pressure, the volume of the gas adsorbed is independent on the pressure. Only at lower pressure it is dependent. Volume of the gas adsorbed is directly proportional to the pressure of the gas. So this is the Langmuir's adsorption isotherm. So today we explain the Langmuir's adsorption isotherm. The some important terms we have discussed: what is adsorbent, what is adsorbate, what is adsorption process. Generally, adsorption process is carried out on the surface of the adsorbent. Many such processes are takes place. The very good example it is charcoal. Onto the charcoal, the liquid molecules get adsorbed. The example it is adsorption of acetic acid on charcoal. Now on the solid surface, the gaseous molecule can be adsorbed. Particularly in the manufacture of sulfuric acid on the surface of the platinized asbestos, the sulfur dioxide gas and oxygen gas get adsorbed. So on the surface of the adsorbent, such reactions are takes place. So adsorption, it is a very important process. So in this way, we has been discussed here the process of the adsorption. So now I would like to stop the lecture.